In exercise 2C, we're going to look at the applications of the trig identities. Now, as the name suggests, what you're learning in this exercise is how to apply those trig identities. You will only get the maximum benefit out of the questions in this exercise if you actually know the trig identities. You have the trig identities revised for you back on this page. However, can I strongly suggest, if you find yourself referring back to this page throughout exercise 2C, then it is time to stop, go back to this page and put more effort into learning these. If all you're doing through exercise 2C is referring back to here, you're not getting the most out of doing the questions. You need to be able to look at the questions in 2C and have these identities come to you without having to look back and see if there's something here on this page that will help you to move on. You see the poster in my room that says something about believing in luck, and the harder you work, the more luck you get. Well, we could think about that here in exercise 2C. Your luck with getting through 2C will depend on how much hard work you've done to learn the identities. And in fact, it is, excuse me, it is not luck at all. Your success in 2C depends ultimately on how much you know. And we want to be more than successful with 2C. We want to learn how to do these questions, identify problem areas for ourselves, and that will be different for everyone, and build our confidence so that when we see these questions in the future, we know that we can recall these identities, and we'll be able to work through unseen questions. So the application of trig identities really shows itself in two areas. One is calculus, and that's really easy to identify, the integral of cos squared or the integral of sine squared. Now, that's why the question that appeared in the topic test was a little bit off-putting, because normally we would be using this technique that we're going to learn here in that situation. That's not to say that question wasn't able to be done the way it was suggested in that question, because you could do it that way. But normally, excuse me, you'll see a question with the integral of sine squared or cos squared, just like it says here. Then you will hopefully make the connection back to trig identities, and you need to replace this expression that they're asking you to integrate. The other area is just straight out, and when I say geometry, when we say geometry, we just mean you may be given a triangle, and information's given in the triangle, and you have to use that to answer the question as presented. Let's have a look then at this example. So you can see here I've written we only have a limited number of functions, styles, that can be actually integrated. And you can see I've written those up. We know how to integrate sine, we know how to integrate cos, sec squared. We know how to integrate this, which may appear in the geometry style questions. We know how to integrate this and this. So nowhere do we have the integral of cos squared. We know that cos squared can be written as 1 minus sine squared. It's not going to be helpful to replace a cos squared and introduce the complication of a sine squared, so we'll leave that one. We also know that cos squared could be written as a half plus a half cos 2x. Now that's much nicer. And you can see that I have done that there. So it started with the integral minus pi on 6 to pi on 6 of cos squared x plus pi on 12. We keep the same limits of the integration, and we've just simply replaced cos squared this. It's a little bit complicated, but we just replace it with a half plus a half cos 2 times what's in that bracket. Then we have to think about integrating this. No problem integrating a half, but we do have to have a little think about what's going on here. We know that cos, to start with, I guess we'll just leave the half for a moment. Can't really see what role that's playing or what where it may have come from, not yet. We know that the cos comes from a sine, so we know that we possibly had sine 2x plus pi on 12, and you could actually start there. If I was differentiating, think about this now, if I was differentiating sine of 2x plus pi on 12, I might just write that as sine 2x plus, well, distribute the 2 in the bracket, and you get pi on 6, just so that you can see, if I was differentiating that, it goes to cos of this 2x plus pi on 6 times differentiate inside here, which is a 2. So you would actually get 2 cos, and take the 2 back out, x plus pi on 12. Now, is that what we were asked to integrate? It would have been nice if this had been a 2 cos 2 x plus pi on 12, but it's not. Remember I said we couldn't see initially where that half came from, but we can work out now that that half meant that there must have been a 1 on 4 sitting here. So the 2 cancelled with the 4, so there was a 1/4, there was a 1/4 that was brought down through that process. So we can go on now and say half would come from a half of x, or x on 2, plus a quarter of sine 2 outside of x plus pi on 12. And you may have your own method for working out the primitive function or undoing integration. But sometimes I find for myself that in more difficult situations I break it down piece by piece and think about what was differentiated to give this, and work through the differentiation, work through it on the side. Okay, that's not a very nice question at all, but it's not impossible. It does, however, require a very high degree of carefulness, if there's such a term. So let's have a look. So we've got our integral x on 2 plus a quarter sine 2x plus pi on 12 from minus pi on 6 to 6. So we're at the stage of substituting. So x on 2 I've written as, just so you can see the substitution, a half, I've taken the half out, times x, which is pi on 6. A quarter sine 2 times, and putting the x value in, pi on 6 plus pi on 12, minus a half again, so we're subbing now the negative pi on 6, a half times negative pi on 6, plus a quarter sine 2 negative pi on 6 plus pi on 12. There's nothing difficult. It's messy. It's got a lot of terms in it. It's going to have a lot of negatives in it. It's not like any of this work now is difficult. However, I would think that if you're not showing every step here, you are really putting your answer at risk of not being correct, because there are so many places where you could make a slight mistake, which then will be very costly. It'll be costly time-wise, and it'll be costly mark-wise. So keep that in mind. It really does pay to show every little step. So on the next line, I've just simplified the half pi on 6. I've done this little simplification of sine of 2 times pi on 6 plus pi on 12, and you can see I've done that here in green. And again, I think it's really worthwhile doing all those steps. Add what's in the bracket, which you can see came to pi on 4, multiply it by 2, and it becomes pi on 2. So you can see the simplification of that appearing here. Then go on and do a similar thing in this bracket and the second bracket, and you can see that I've simplified that here in black, and it comes out at minus pi on 6. So pi on 12, a quarter, because sine of pi on 2 is 1. Sine of minus pi on 6, you can see I did a little calculation down here for that. I'm down in the fourth quadrant, or negative pi on 6. So I know that sine down there is a negative. I'm drawn a little triangle for pi on 6, sits in that spot, and sine is a half. So I know that it has to be negative a half. I really encourage you to also do all these little steps. It's best to practice it now. Try not to be taking shortcuts, because it reinforces so many other little rules. You're forcing yourself to do some fraction work here. You're forcing yourself to recall these rules. And the more you do that successfully, the more ingrained the rules become. So doing some simplification, then we get eventually pi on 6 plus 3/8 is our answer. Certainly not nice. I'll stop the video there and do the next example in another video.